So, welcome to my dear friends and learners. In the last lecture, we have understood the velocity triangle of turbine. One is inlet velocity triangle, where the C1 is the absolute velocity of the steam which is entering into the moving blade, and while the blade is start to rotate, so then the relative velocity of the steam, which is v1, so basically the velocity of the moving blade and the relative velocity of the steam, that resultant will give the absolute velocity of the steam which is entering into the moving blade. And similarly, this v2 is the relative velocity of the steam while it is exiting from the moving blade, and this c2 is the absolute velocity of the steam at the exit. And similarly, the resultant of the uh, uh, moving blade velocity and the relative velocity of the steam at the exit will give the absolute velocity of the steam at the exit. So this concept is already clear. And as I told, this this analytics, we considered a set of fixed blade and a set of moving blade, so which is considered as a single stage. Okay, in practical, this single stage, and also as I told in the earlier lecture, that pure impulse turbine or pure reaction turbine is, there are several disadvantage. So due to that reason only, it is always advisable to design the or consider the turbine design. During the turbine design, uh, the rotation of the rotor will be responsible for reactive force as well as the impulsive force. That means, that's why the turbines are called impulse reaction turbine. So the movement of uh, the rotation of the turbine is, some extent it will be uh, coming from the impulsive effect, and some portion of the motion or the torque is responsible for the reaction. Okay, so when the reaction is concerned, so we have to consider the relative velocity, and when the impulsive effect is to be considered, that time we have to consider the uh, absolute velocity of the steam, because with absolute velocity, it is directly when the blades are still stand, it is not rotating, that time suddenly that high pressure steam jet is striking on the moving blade, and a impulsive effect is generated, which is giving the motion to the turbine. And once motion is considered, then the steam velocity is become the relative speed, which is v1 at the inlet and v2 at the outlet. And with the, and once it started to rotate, Then with the effect of this V1, some reaction force is generating, and that also adding further adding the torque to rotate the turbine. Okay, so once this calculation whatever we have did earlier, that is due to considering purely impulsive effect, okay, for an impulse turbine. But as I told, it is there are several advantage and disadvantage of both reaction and the impulse turbine. So better to consider the both effects. Okay, that's why the practical steam turbines are impulse reaction turbine. Okay, so if you see the practical turbines are used in thermal and the nuclear plant, those are multi-stage impulse reaction turbine. Okay, and it is always better to have increased efficiency of the turbine if we can the 50% reaction is used. That means the turbine rotation 50% is coming from the reactive force and the 50% will be coming from the impulsive force, and both combining together it will, because uh, that will always better, and we will while we will be calculating the efficiency we will understand that. Okay, now we will how what is the condition, what is the mathematical inference that we can establish, or we can consider that exactly the torque produced by reactive force and the impulsive force are equal. Okay, so as I told, the impulsive force, the contribution due to impulse is basically due to the absolute velocity of the stream. So in this case, in the inlet it will be C1, and at the outlet it is C2. Okay, this is the C2 or this is the C2, and this is your CW1 and this is your CW2, which are cos component. So the resultant, the del CW2, which is basically CW1 minus CW2, those are C1 cos component, that means cos alpha 1 minus the CW2. The CW2 is C2, this is C2, no, this is C2 and this is your alpha 2. So C2 cos alpha 2, cos alpha 2. So this component basically it will contributing the impulsive effect for the turbine, because we are considering the absolute velocity. And in the earlier discussion we understood that whenever we are considering the reactive contribution, we have to consider the relative velocity, which is v1. So if that is the case and the torque the velocity component, the steam velocity component, by which is causing the torque by reaction, if that is C del C V, which is basically the cos component of V1, or you can write C. So this component is in this direction, which is V1, which is V1 uh, cos beta 1. Okay, and this component, that is, this is your V2 and this is your beta 2, this is your beta 2. So this component is V2 cos beta 2, and your del CV, okay, or sorry, del VW, which is nothing but, so this, from this drawing, your C, your VW1 is greater than VW2. So this is VW2 minus VW1. So what is VW2? VW2 is basically V2 cos beta 2. So this is V2 cos beta 2, and minus VW1 is their opposite direction. So it is, because your VW2 is in this direction and VW1 is in this direction. So that will be V1 cos beta 1, cos beta 1. Okay. Now from this expression and from this expression, so this part, so this, now this CW, del CW is coming from the impulsive effect, and del VW, it is coming from the reactive effect due to reaction. Now if both are to be equal 50%, the degree of reaction is 50% and remaining is from impulse effect, then this del CW should be equal to del VW. How it is possible from these two equation? If your C1, this C1 should be equal to V2, and your alpha 1 is equal to this, alpha 1 should be equal to beta 2, and in the remaining part C2 should be equal to V1, and your alpha 2 should be is equal to beta 1. Okay, this is the necessary condition. With this concept, the practical turbine design started. Means from there only we have to start. Okay. If you consider that the absolute velocity of the steam at the inlet is equal to the relative velocity of the steam at the outlet, and the relative velocity of the steam at the inlet, if it is equal to the absolute velocity of the steam at the outlet, and the alpha 1 is equal to beta 2 and alpha 2 is equal to beta 1, then your impulse reaction turbine can be designed so that the impulsive effect is contributed 50% and the reactive force contributed 50% for the rotation, for the to produce the torque of the turbine. We will discuss one by one, because if the mathematical things are clear, then your concept will be very, very clear. Okay. Another thing I told, the turbines should be uh, uh, multi-stage. Why so? In case of single stage turbine, if you see the earlier one slide here, this is a single stage impulse turbine. So this pressure is the steam generator pressure, and this pressure is the condenser pressure. So there is a huge uh, pressure drop. Okay, and once there is a pressure drop, that is definitely increasing the velocity. Okay, and this high velocity is causing the higher friction loss. Okay, and once there is a high rotational speed or angular speed, so this will cause the centrifugal loading. Small residual unbalance can cause huge vibration, so to handle that situation will be very difficult. Okay, so in case of a single wheel impulse turbine, the speed can go up to 30,000 rpm. You know, the design of the bearings to handle the radial and axial thrust, um, those are very difficult. So to avoid this problem, okay, more than one sets of nozzle blades and rotors, those are used. So if you do that, so in case of sudden pressure drop, or in case of sudden velocity change, the thermodynamic changes will be taking place gradually, which will uh, reduce the losses and uh, enhance the mechanical design much more easier. Okay, so the process or the assumption or the consideration through which this can be done is called the compounding of steam turbine. Okay, so those things there are, you can do the pressure compounding, you can do the velocity compounding, you can do the pressure or velocity compounding both together. Okay, so these things we will go in details one by one in the subsequent discussion. So what we understand from today's discussion, that the practical steam turbines are neither impulse nor reaction, the mix of both, and always it is advisable that the 50% should be contributed by impulse, and 50% it will be contributed for by the reaction. And once you are considering the impulse effect, definitely you have to consider the absolute velocity, and once you are considering the reaction, you have to consider the relative velocity of the steam. And this 50% contribution is possible, and mathematically we have established that the absolute steam velocity at the inlet should be the relative velocity of the steam at the outlet, and vice versa, and the angles, corresponding angles, are also to be identical. This means from there we can conclude that the shape of the fixed blade and the moving blade, or the nozzle uh, geometry, and the passage between the moving blade, both should be identical. And to avoid the huge pressure drop across the steam generator and the condenser, rather than having a single set of nozzle and the moving blade, if you can do it by several stages, then the handling of such loss and the turbine speed, all these things can be handled in an uh, fruitful manner. Okay, so these things we will discuss in the subsequent lectures, because today it is late night. Still I have to prepare dinner and I have to take dinner. Thank you so much. Thanks for your patience.